Hello everyone, my name is Stu Adler. Welcome back to Introductory Lectures in Thermodynamics. So far, most of our focus in this course has been on understanding the energy and entropy of groups of molecules, what internal energy and entropy really are, and how they're related to other measurable properties of substances. This episode marks our first step toward putting this understanding to some practical use from the standpoint of chemical engineering. As mentioned in episode A1, the history of thermodynamics, including the term thermodynamics itself, is rooted in analysis of energy conversion processes. Thus, one major application of thermodynamics is in the analysis of process efficiency. Today's cartoon is based on a famous perpetual motion machine first proposed in the 12th century by the Indian mathematician Bhaskara II. It's based on the principle that forces, applied further from the center of a wheel, will exert greater torque. Thus, by maintaining the asymmetrical position of weights on a wheel as it spins, the unbalanced torque continuously drives the motion of the wheel forever. So, does this really work? This cartoon by Scott Smitelli provides one particular hipster's view, which is that it will, as long as you keep paying the electricity bill. He's right, of course. But the question I'd like to address today is whether we can take our understanding of how much work we can extract from a real process a bit deeper than this. Although process efficiency is a huge topic, which itself is a subject of whole courses, I think it's valuable to introduce at least some of the key principles of process efficiency analysis, including the concept of reversible work and the linkage between efficiency loss and entropy generation. Besides providing a theoretical best-case scenario for guiding process design, this type of analysis can be used to analyze which steps in a process cause the greatest efficiency loss, thereby aiding optimization. Before going on, I need to make a brief comment about sign conventions for heat and workflows in process analysis. In first law analysis of substances or phases in closed systems, we commonly employ a universal sign convention for heat and work. With this convention, heat or work entering the system are defined as positive, while heat or work exiting the system is negative. However, in analyzing a process, what we consider to be the system for purposes of first law analysis may vary. For example, heat or work might exit one unit and enter another. In this case, it's not possible to stick to a universal sign convention for the first and second laws. For this reason, it's common practice to adopt a local sign convention, defined in the process description or drawing, in which case the first and second laws must be modified accordingly. For example, in older thermodynamics textbooks focused on process analysis, it was common to define positive heat as inward and positive work as outward, in which case delta U equals Q minus W. Note this is not the same issue as whether heat or work itself is positive or negative in value. The issue here is how the variables W and Q are defined, and how this affects the form of the first law. Okay, with that issue out of the way, let's focus in this episode on one particular type of energy conversion process, called a heat engine, which converts a thermal energy source into work, or vice versa. To begin, imagine we have two reservoirs, maintained at uniform and constant temperatures, TH and TC, where TH is greater than TC. If provided a mechanism, heat will tend to flow irreversibly from hot to cold, creating entropy. The purpose of a heat engine is to harness this tendency of nature and extract some work. Our goal for this episode is to understand the maximum amount of work we can extract, and to analyze the efficiency of a real heat engine. Although we're usually interested in far more complex sources of energy, for example fuels, heat engines are useful conceptually for understanding the limits placed on energy conversion processes by the first and second laws. The first question we should probably address is how much work can our process theoretically produce? To answer this, let's start by considering the first law for a steady state or cyclic process that does not have any accumulation of energy inside the process. In this case, we can say that 0 must equal Q1 minus W minus Q2. Thus, no matter what we do, energy conservation places a limit on how much W can be, based on Q1 and Q2. But are there any other limitations? To see, let's also express the second law. However, to do this, we need to be clear about the temperature at the boundaries of our process. In the context here, we'd like to understand all the possible irreversibilities that our process could have. Thus, let's draw our system boundary such that heat entering or exiting our process occurs at temperature TH and TC, respectively. In other words, any temperature gradients that occur as part of the heat transfer to or from equipment in our process is considered part of our process. With that general assumption, the second law states that 0 must equal Q1 over TH plus Sgen minus Q2 over Tc, where Sgen is greater than or equal to 0. Rearranging and solving for W, we find that work output is maximized when Sgen is 0, in which case W equals Q1 times 1 minus Tc over Th. This implies that as Tc approaches Th in absolute temperature, the fraction of work we can recover from the heat source gets less and less. Thus, even if we have a very high temperature source, we also need a low temperature sink to make any use out of it. To take a specific example, the Stirling engine I showed you in episode A1 sat on top of a cup of coffee that was probably about 60 degrees C. Assuming an ambient temperature of 20 degrees C, the ratio of the maximum possible work divided by the heat flow from the coffee is 1 minus 293 over 333, which is 0.12. In other words, no matter how good our process is at converting heat to work, only about 12% of the heat emanating from a source at 60 degrees C can be converted to work if we reject the remaining heat to the reservoir at 20 degrees C. Now imagine we reverse the direction of our heat engine, turning it into a heat pump, which takes heat out of the low temperature reservoir and delivers it to the high temperature reservoir. Rewriting the first and second laws, and solving for W again, we find that the minimum amount of work we must input occurs when Sgen is 0, in which case the work is, again, equal to Q1 times 1 minus Tc over Th. In other words, the work is equal and opposite for a reversed process only if Sgen is 0. This amount of work is called the reversible work, or Wrev, since it corresponds to the limit of a reversible process where no entropy is generated. The ratio of the reversible work to Q1 is called the Carnot efficiency, named after the 18th century French thermodynamicist Sadi Carnot. This is a somewhat unfortunate name for this quantity, since it's probably misleading to think about this as an efficiency. The word efficiency implies a ratio of what you can achieve versus what is theoretically achievable. What we're saying here is that even if our process is 100% reversible, only a certain fraction of that heat is theoretically recoverable by any means. Thus, Q1 is probably an inappropriate benchmark for defining efficiency. Instead, the relevant benchmark for a heat engine is Wrev. That was a monumental realization to steam engine designers in the 1800s. Sadi Carnot is widely considered to be the father of classical thermodynamics. He was the first to articulate the second law in some form, specifically that heat can only move spontaneously from hot to cold, even before the first law was fully understood. His work was motivated primarily by the desire to better understand steam power. However, the properties of steam were not well understood in the 1820s. In order to bound the maximum possible work one can obtain from a heat source, he theorized about heat engines based on cyclic expansion and contraction of an ideal gas. This work was published in 1824 under the title that translates roughly in English as Reflections on the Motive Power of Fire and on Machines for Extracting that Power. What is amazing about his work is that he correctly surmised the importance of reversibility more than a decade prior to the discovery of entropy as a property. Though his work was not well appreciated at the time, it had an enormous impact on later work by Clapeyron, Clausius, and Lord Kelvin, who in the 1830s through the 1860s put Carnot's original work on firmer quantitative footing, based on the properties of ideal gases. This work included the articulation of entropy as a property and the second law as we understand it today. Carnot's gas recompression cycle works as follows. Imagine we have a closed piston cylinder assembly with an ideal gas at initial pressure P1, which is in equilibrium with a heat source at temperature T sub H. In step A, we expand the gas isothermally and reversibly to lower pressure P2, absorbing heat at temperature TH. Then in step B, we continue to expand, producing additional work. But instead of absorbing more heat, we expand reversibly and adiabatically, lowering the pressure further to P3 and the temperature to Tc. Then in step C, we isothermally and reversibly compress the gas to pressure P4, consuming work and rejecting heat at temperature Tc. Finally, in step D, we adiabatically and reversibly recompress the gas back to pressure P1 and temperature Th. In this strategy, pressures P2 and P4 are chosen to ensure that the adiabatic expansion and compression steps hit their desired temperature and pressure targets P1 and P3 at Th and Tc, respectively. The first to sketch these transformations on a PV diagram was Émile Clapeyron, who in 1834 analyzed this process quantitatively based on the properties of an ideal gas. On a log P versus log V diagram, the Carnot cycle looks like this. In step A, the pressure drops from P1 to P2 along the TH isotherm, which has a slope of -1 on a log-log plot, since the gas is ideal. Then in step B, the pressure drops more steeply to P3, as the temperature also drops to Tc. Since the transformation path from state 2 to state 3 is adiabatic and reversible, it follows a line of constant entropy, S3. In step C, the gas is compressed isothermally to pressure P4 along the Tc isotherm. Finally, in step D, the gas is returned to pressure P1 and temperature Th by being compressed reversibly and adiabatically at constant entropy, S1. The same process on a Ts diagram looks like this. Although all 4 steps in the process involve reversible transformations of the gas, and thus no entropy generation, steps A and C involve absorption and rejection of heat, and thus a change of entropy. Based on the paths outlined here, let's calculate heat and work. For purposes of analysis, let's assume we know Th and Tc. Let's also define P1 and P3 as the physical limits of our cycle. Finally, for simplicity, let's also assume the heat capacity is constant. This doesn't affect any of our conclusions, but simplifies the mathematics greatly. Before jumping into the second law analysis, let's briefly review some of the relationships we derived previously for internal energy, enthalpy, and entropy of an ideal gas. Recall that the internal energy of an ideal gas is independent of pressure and given by the integral of Cv dt from a reference temperature to the desired temperature. Likewise, the enthalpy is given by the integral of Cp dt. The entropy depends on both temperature and volume or pressure, and can be expressed as an integral of Cv over T dt plus R log of the volume. It can also be equivalently expressed as the integral of Cp over T dt minus R log of the pressure. Note that these statements are equivalent and can be interrelated by substituting the ideal gas law for volume or pressure and the fact that Cp is equal to Cv plus R for an ideal gas. In our problem here, it's probably easiest to use these two forms, since we must examine a closed system balance involving internal energy, but we're working with pressure as an independent variable. Starting with step A, the first law states that delta U is Q plus W. But since delta U is 0 for an ideal gas along an isotherm, this implies that heat and work are equal and opposite. Note the sign convention used here. Heat is defined as positive inward, while work is defined as positive outward. Thus QA equals WA, with both being numerically positive. Since the transformation is reversible, the second law tells us that delta S must be QA over TH. Substituting the state relationships I just showed you for entropy versus pressure, we obtain a value of QA shown here, which is also the work due to the first law. Although we've specified P1 as an independent variable, we don't yet know P2, so to actually calculate heat and work here, we would need to first solve for P2. Let's come back to that in a second. For step B, which is adiabatic, the first law tells us that delta U equals work. Substituting our state relationship for U versus T, the work is given by Cv times Th minus Tc. Meanwhile, for an adiabatic and reversible transformation, which has no heat flow or entropy generation, delta S is 0. Thus, we can relate the temperature and pressure changes going from state 2 to state 3. Substituting TH and TC for T2 and T3, we can solve for P2 versus P3. This is where we get P2 to complete the previous expression. Basically, this is giving us the point on the PV diagram where the S3 isentropic line intersects the TH isotherm. One thing you might wonder is how Clapeyron, who didn't yet know about entropy, derived the transformation path from state 2 to state 3. But even without entropy, if we imagine the gas remains in a continuous state of internal equilibrium, with well-defined pressure and temperature obeying the ideal gas law, which is how reversibility was originally defined, we can still solve it. The key is to recognize that without heat, du is equal to minus dw along the transformation path. Thus Cv dt is equal to minus Pdv. Converting dt using the ideal gas law to dv and dp, and then simplifying, we find that along this transformation path, d log p, d log v is equal to minus k, where k is the ratio of Cp to Cv, a number usually around 1.4 or so for most gases. Integrating, we can solve for P2 versus P3 with the same result we got previously. In fact, it was this more mechanistic view of adiabatic reversible expansion of ideal gases that helped Clausius come up with the idea of entropy, which Boltzmann finally explained in terms of molecular multiplicity. Okay, so enough with the history lesson. Returning to the Carnot cycle, we can repeat all the steps we just did for steps A and B to determine the heat and work for steps C and D, including finding the unknown pressure, P4. This results in the expression shown here. Note that the work input in step D is the same as the work output of step B, so cancels in the net work. But the input of work in step C is less than the work output of step A, so the cycle does produce a net amount of work. We can see this by adding up all the work inputs and outputs. Since B and D cancel, substituting P2 and P4 in terms of P1 and P3, we end up with the total work output shown here. Comparing to the net heat input in step A, we can see they differ by a simple ratio of TH minus TC divided by TH, which is the Carnot ratio. So there you have it, a specific process involving compression and expansion of an ideal gas that embodies the general principle we derived earlier. This also shows that by imposing reversibility of all steps within a process, we guarantee overall reversibility of the process as a whole. One neat graphical way to visualize what's going on here is to examine the transformation path on a TS diagram. As I showed you earlier, the transformation path of the fluid in a Carnot cycle can be viewed as clockwise rotation around a square box, with TH at the top, TC at the bottom, S1 on the left, and S3 on the right. Examining the expression we just derived for the heat input in step A, it corresponds graphically to the area under the TH isotherm, shown here in red. The heat output in step C is likewise given by the area under the TC isotherm, shown here in blue. Thus the work output, which is the difference between Q in and Q out, is the difference between these two areas, which is the area inside the box, shown here in green. This graphical trick turns out to be generally valid. No matter how complicated the transformation path of the fluid is, as long as it forms a closed cycle that returns to its starting point, the work produced per cycle is given by the area surrounding the path on the TS diagram. Okay, so the next question is what happens if our process is not 100% reversible? In this case, Sgen in our original generic formulation of our problem is not 0, meaning less work output. What things can cause entropy generation? And how does this generation manifest as lost work? As I'll show you in a moment, there are basically two ways we can generate entropy. The first is that our process itself can have inherently irreversible steps in it. This means that no matter how slowly and carefully we try to do something, we cannot avoid the generation of entropy. The other cause of entropy generation is a theoretically reversible step that is implemented in a way or a rate that causes irreversibility. To better understand both these classes of irreversibility, let's take a closer look at a Stirling engine, in particular the version I showed you in episode A1. Shown here is a sketch of the inner workings of this particular engine, which is based on the expansion and contraction of a sealed volume of air. The bulk of the air is held in a short, wide, cylindrical container, exposed on the top and bottom surfaces to a hot and cold reservoir, respectively. Inside the container is a lightweight piece of insulating foam called a displacer, attached to a rod controlled by the outside flywheel. The purpose of the displacer is to move the air back and forth between the top and bottom surfaces. Note that the displacer is not a piston. The whole idea is that the air can easily get around it when it moves up and down. As the gas heats and cools, it expands and contracts, pushing or pulling on a small drive piston, which is inside a smaller cylindrical appendage attached vertically from the top plate. This piston is attached to the same flywheel as the displacer in such a way that their motion is 90 degrees out of phase. The way the engine works is as follows. Initially, the gas is at its minimum temperature and volume, in contact with the low temperature side of the cylinder. Due to previous motion of the flywheel, the displacer sweeps the gas to the hot side of the container, where it begins to warm up. Initially, this heating is approximately isochoric, since at this point the piston is close to the minimum in its range of motion. But as the gas reaches higher temperatures, this heating becomes approximately isothermal as the piston begins moving upward and extracting work from the gas as it continues absorbing heat. Finally, the gas reaches its maximum volume and temperature, at which point the displacer sweeps the gas back over to the cold side of the container. The gas then cools approximately isochorically, and then approximately isothermally, until it reaches its original state. Note that it doesn't matter which side of the container is hot or cold. As shown here, the polarity of the temperature difference only affects which direction the flywheel rotates under steady periodic operation. To analyze the efficiency of this engine, let's assume an idealized Stirling cycle, as shown here. In this idealization, the heating steps I just showed you are approximated as distinct isochoric and isothermal steps A and B, and likewise for the cooling steps C and D. However, due to heat transfer limitations, both inside and outside the reservoir, let's assume the actual maximum temperature reached by the gas, Th prime, is less than Th. Likewise, the minimum temperature of the gas, Tc prime, is higher than Tc. These temperature differences are what drive heat transfer during the isothermal steps. With these assumptions, here's what the idealized Stirling cycle looks like on a PV and a TS diagram. Note that since the closed loop of the cycle falls inside the bounds set by Th and Tc, we already expect a less efficient process than a Carnot engine. This implies that the assumptions we've made about this process involve irreversible process steps. Let's take a closer look by analyzing each of these steps in the process individually. Starting with step A, since there is no PV work for an isochoric transformation, the first law tells us that the heat is given by delta U, which is Cv times the total temperature change of the gas, Th prime minus Tc prime. Likewise, delta S is Cv log Th prime over Tc prime, since the transformation is isochoric. According to the second law, this total change in entropy, which we already know from the endpoints, must be composed of heat flows plus entropy generation. In order to capture all of the heat transfer as part of our process, let's draw the control volume such that the heat enters the system at constant temperature Th. This means that the integral of dqa over T is just qa over Th. Taking the difference, we find we have non-zero entropy generation for this step. Note that for this step, even if heating is done slowly, such that Th prime approaches Th and Tc prime approaches Tc, the entropy generation is non-zero. Turning to step B, which is isothermal, we know delta U equals 0, since it's an ideal gas. Thus heat and work are equal and opposite. Since we know temperature is Th prime along the entire expansion, we can calculate work directly as the integral of P dV, positive since work is defined as outward in this case. Substituting the ideal gas law, we can obtain work and heat. Since we know the end states of volume from the geometry of the engine, we can calculate delta S as well. Examining the second law, this delta S will be composed of the heat flow divided by the boundary temperature plus generated entropy. Taking our control volume boundary to be at the reservoir once again, the integral of dQB over T is just equal to QB over TH. Taking the difference, we see that this step is also irreversible, generating entropy at a rate proportional to the difference between TH and TH prime. To better understand how the entropy is generated in steps A and B, shown here is a sketch of the temperature as a function of time as the system evolves from state 1 to state 3. Since in this case we've drawn the system boundary at the point where the process meets the reservoir, this difference in temperature exists inside our system. As we discussed in a previous episode, whenever heat flows under a temperature gradient inside our system, we will generate entropy. The differential rate of entropy generation, dsgen, is given by the differential heat flow, dq, times the difference in reciprocal temperature across the gradient. Breaking this integral into two parts for steps A and B, and then substituting the differential form of the first law relating heat flow to changes in temperature or volume, we can solve the integral for the total generation of entropy due to these gradients. The result is exactly the same as we calculated previously for these steps as a whole. In other words, we can blame all the entropy generation in our idealized cycle on this heat transfer process. Note that as Th prime approaches Th, the entropy generation in step B goes to 0. This is an irreversibility we could theoretically try to minimize by our choice of equipment or operating conditions. For example, reducing the gradient by improving the rate of heat transfer. In contrast, the gradient in step A is inherent to our process, something that will always occur whenever we heat something by exposing it to a reservoir at a fixed temperature. In the Carnot cycle, we never actually heated or cooled the gas to change its temperature. The temperature changes were all done adiabatically, so that all heat transfer could be done isothermally, at the reservoir temperature. But here this gradient is an inherent part of our process, so there's nothing we can do to engineer it away other than choosing a different process. Steps C and D are nearly identical to steps A and B, so I won't belabor the derivation further, other than to say we need to be careful of sign conventions on all the work and heat flows. The result is that steps C and D also involve heat and work and generate entropy in a very similar way as steps A and B. Putting everything together, we find that the work produced is proportional to the difference between the maximum and minimum temperature achieved by the gas times R log of the volume ratio between the minimum and maximum volume. Rather than calculating the efficiency based on the incoming heat flow, which we already argued is a meaningless comparison, let's instead benchmark our process by comparing to the highest theoretical amount of work we could have extracted based on a perfect Carnot engine. This is given by the total heat flow into our process multiplied by the Carnot ratio, 1 minus Tc over Th. Substituting our results for QA and QB, we get the amount shown here. Taking the difference, we can calculate the work lost by irreversibilities in our process. Note that this is not a loss of energy. This is a loss of work that ends up as additional heat going into the low temperature reservoir. Recall that according to our previous generic analysis, the reduction in work due to entropy generation is given by Sgen times Tc. In this case, we have a detailed breakdown of the entropy generation caused by heat transfer in each step, so should be able to calculate this. Adding up the total entropy generation caused by temperature gradients in our process and multiplying by Tc, we get a total value in exact agreement with the lost work we just calculated. The difference is that we have a detailed breakdown of how much entropy each process step generated and why, and how this affected work. Using a TS diagram once again, we can try to visualize what's going on graphically. Our idealized Stirling cycle is shown here. As we discussed, the work produced by this cycle is equal to the area inside the region traced by the fluid along its process path. Some of you might recall that the area of a parallelogram is the height times the base, which is Th prime minus Tc prime times S4 minus S1, which is R log of V3 over V1. so our area identity seems to apply here. In comparison, shown here is the area corresponding to a Carnot cycle operating between TH and TC, having the same total consumption of heat from the high-temperature reservoir. As you can see, the work produced by our process is a lot lower. For example, returning to our Stirling engine from episode A1, the geometry is such that V3 over V1 is only about 1.02. Assuming pressures developed are small, this implies a temperature difference of Th prime minus Tc prime of only about 6 degrees C in operation. Plugging in numbers, the ratio of total work produced by the idealized cycle to the theoretical work based on Carnot considerations is only about 5%. That's 5% of the theoretical work, which in turn is only 12% of the heat, as we found out earlier. In other words, we're only capturing about 0.6% of the total heat flow from the coffee. Even this is an upper estimate, since in reality the actual transformation path of the gas looks more like this, due to the rotational coupling of the displacer to the piston movement. There's also friction. These irreversibilities add further to the entropy generation, which in turn occurs additional lost work. As I'll show you in the next episode, we can generalize this linkage between entropy generation and lost work to help us diagnose where inefficiencies exist in a process. The use of second law analysis for this purpose is sometimes called lost work analysis or exergy analysis, and is an incredibly useful and practical application of thermodynamics in chemical and mechanical engineering.